It's mathematical induction. What this is another type of proof. You've proved things, a lot of things, using deduction. Right? Your geometry problems are all using deduction. So to deduce something is to start from a whole heap of facts, things you know that are true. And from that, you deduce something. You say, oh, look, okay, I know that angle's this, that angle's this. So, and I also know that the angle sum of a triangle is this. Therefore, I can deduce the size of this angle is whatever. That's a deduction. What we're going to look at is an induction. And to induce a proof, there are some key steps. But basically, it works on the idea is what we're trying to prove, we assume is correct. Right? So we don't actually know it's correct, we assume it's correct, and from that we induce the proof. So it works a bit like this. The first step, now you don't have to write step one, but the first step is you go and prove the result's true for the first case. So usually n equals 1, but it might not be n equals 1, that you might be proving it true for even numbers. In that case, the first case would be n equals 2. So just make sure you read the question carefully. Now, whilst I say you don't write the words step 1, you do write down prove the result's true for n equals 1, because this is a proof, just like geometry. You've got to spell it out so the reader can follow your solution. They know exactly what you're doing. So once we've proven that, in comes the assumption. So I'm going to assume whatever it is we're trying to prove is true for n equals k, I usually use, and you'll find a lot of people use k, where k is some positive integer or whatever condition matches the question. If it was an even number, we'd say, oh, well, k where it's some even number, or we just basically match what it is we're trying to prove. Then we go and prove it true for the next case, so the next number. So we assume it's true for a case, and then we prove it. Using that, we prove it's true for the next case. Then the inductive step comes along. And it's surprising how often people don't bother with this. But this is the key that pulls the proof together. Okay? It's important that once you've done your proofs, you make this conclusion, because this is what's going to allow you to induce the solution. And so you note something along the lines that, well, hence it's true for n equals k plus 1. But, and that's why I've bolded it, if it's true for n equals k, because remember, n equals k was an assumption. If I've assumed it's something that's not true, then my proof's no good. So my proof that it's true for n equals k plus 1 is only good if it is indeed true for n equals k. Now, using that idea, I can induce the solution, because we go back to what we did in step 1. Well, hang on, I proved it was true for n equals 1. So what I then proved was it's true for k plus 1 if it's true for k. So if it's true for 1, it must be true for 1 plus 1, 2. So I now know it's true for 2. If it's true for 2, then it must be true for 2 plus 1. 3. If it's true for 3, and so on and so on and so on. So we induce, therefore, that, it's fair enough to now say, well, it's true for all integers, or whatever the condition we are. There's basically 3 types that we look at. The first type we're going to look at is a series type, which makes sense, seeing we're in the topic of series. So it's not an arithmetic series, it's not a geometric series, it's just some other number pattern. And this number pattern is the odd numbers squared. And what we're being told is that a formula to work out the sum of the odd numbers squared is this: 1/3 n, 2n minus 1, 2n plus 1. And they want us to prove that this formula does indeed work. All right, so first step, I'm going to prove it's true for the first case. So the first case is n equals 1. There's my general term. Right? So they've basically written it out and said, 1 squared, 3 squared, 5 squared, up to, and they'll say, right, general term, 2n minus 1 squared. So on the left-hand side, I'll sub into the general term, and I get 1 squared, which is, of course, 1. So our first term, as we we can see anyway from our pattern, our first term there, 1 squared is 1. All right, well, let's sub into the formula, see if we get the same answer. So a third of 1 times 2 minus 1 times 2 plus 1, yes indeed, that also turns out to be 1. So the formula definitely works for n equals 1. So yes, my left-hand side equals my right-hand side. So yes, it is true for n equals 1. Now don't be lazy. It's a proof. So write down these statements. Just like in geometry, you would write down your statements as you're going along. This is a proof. Okay, I'm now going to assume the result is true for n equals k, where k is some positive number. Oh, so not just any number, but in fact a whole number. And I like to write down my assumption so I can see it. And so what it basically is, what I'm trying to prove, but everywhere there's an n, I've just changed it to a k. So now I want to prove it's true for k plus 1. So again, I'll write down what I'm trying to prove. So this time, everywhere there's an n, I'm replacing it with a k plus 1. So 2n minus 1 became 2k plus 1. N is k plus 1. 2n minus 1, that's 2k plus 1. 2n plus 1 becomes 2k plus 3. So it's basically substituting k plus 1 into n. That's what we need to prove. Okay. In this series type, what I basically do is, there's the number pattern on the left-hand side. I rewrite it, but I put in the second last term. Yep. So the term before 2k plus 1 squared was 2k minus 1 squared. Now why do I do that? To highlight something. Now I don't necessarily write this down in my proof, this is just to show you. If you think about it, there's my sum to k terms. And the last one is my k plus 1th term in this series. Well, the sum to k was my assumption. Remember, I assumed that that sum was correct for n equals k. So now all of this plus, 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 dot, 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 I can replace with an algebraic statement because I have assumed that that is equal to a third k, 2k minus 1, 2k plus 1. Okay. And of course, plus then that next term. I now have some algebra I can play with and try and get what it is that they've asked for. The temptation here is to expand the whole thing out. And it will work, but it'll provide more work for you. Always keep an eye on what you're trying to prove, because we already have some common factors there in those two terms. And if you look at what we're trying to prove, it's also one of the factors of what we're trying to prove. So the first thing I'm going to do is factorize that statement and have 2k plus 1 out the front, because what I'm trying to prove has a factor of 2k plus 1. That makes life a little bit easier because inside the brackets here, I've now got a quadratic. Had I expanded the whole thing out, I would have ended up with a cubic. And cubics are a bit harder to factorise than quadratics. There actually is another common factor there that you may not notice. The other common factor there that is also a factor of what I'm trying to prove. And that is 1/3. You don't see it because the second term there of 2k plus 1 is actually 1/3 times 3. So I can factorise the 1/3 out that I need as well. And I do that sometimes because, well, I don't like playing with fractions necessarily. Did I do it this time? Yes, I did. There you go. So I factorised the 1/3 out, and that gives me something a little bit easier to play with, I think. All right, there's not a lot I can do in the square brackets now other than expand out. And let's see what we've got. So 2k squared minus k plus 6k plus 3, 2k squared plus 5k plus 3, which factorises to be k plus 1, 2k plus 3. And if you have a look at what we're trying to prove, we have now got it. They're all the factors in our answer. So what I can now say is that, yeah, hence, that result is true for k plus 1, if it is also true for k. Some people do that. If you don't feel it's immediately obvious what you've done, then at this line here, when you've substituted in Sometimes people write, well, using the assumption or by assumption, I can do that. I didn't in this case because it was just a straight substitution. We'll see some other ones where I might have rearranged the assumption. In that case, I usually highlight because it's not immediately obvious. Hang on, that's my assumption. So it just depends. Again, I guess it's a bit like geometry or any other proof. If you think leaping from one line to the next line in your proof, it's not clear why you've done what you've done, write an explanation next to it. Why did you do what you did? Oh, I did this because of the assumption, or whatever. Okay, now I can induce the solution. I can get that first step and now my proof and tie them together. And I can say, well, hang on, since the result's true for n equals 1, then it's going to be true for all positive integral values by induction. You'll see some texts and some solutions, they have a lovely long answer here where they write something like this. When I was at school, this is what we used to write. Since the result is true for n equals 1, then it is true for n equals 1 plus 1, i.e. n equals 2. And since the result is true for n equals 2, it is true for n equals 2 plus 1, i.e. n equals 3. And so on for all positive integral values of n. You don't need to do that. We're basically saying, look, hey, we proved it for 1, so now I can induce my solution. So it must be true for all of them by induction. All right, here's one in sum notation. So there's my general term. We're saying, okay, we want to add up all the ones from the first term to the nth term, and they reckon that we could just use n on 2n plus 1. Sometimes, if it's not immediately obvious, I like to write out the pattern. So they gave it to me in sum notation, so I write it out. But notice, I didn't write it as a third plus a 15th plus a 35th. On the bottom, I left it as 1 times 3, 3 times 5, 5 times 7, so I can see what the pattern is. And so, oh, okay, on the bottom of each fraction, we've got 2 consecutive odd numbers. So I sometimes see that. All right, well, let's prove it for the first case. On the left-hand side, 1 on 1 times 3, yes, that's 1/3. Right-hand side, I get 1 on 2 plus 1. Yes, that is also a third. So, yep, left-hand side does equal the right-hand side. So it is true for n equals 1. I'm going to assume the result is true for n equals k, where k is some integer. So there's what I'm going to assume. So now we're going to try and prove it true for k plus 1. So there's my pattern. 1 on 2k plus 1, 2k plus 3. By the way, if you write that in sum notation instead of writing the whole thing out, you don't change the general term. Right? The general term would stay the same. It's just you're going to k plus 1 instead of, n plus 1 instead of n. Do you get the idea? Because you're still substituting into the same general term. A mistake people often make when they're using sum notation is to change the general term for the next step. General term hasn't changed, it's just how many terms we've done has changed. So, right, there we go. That's what we're trying to prove. Well, it's the series type. So, first thing I'm going to do is rewrite it as the sum to k terms plus that k plus 1th term, because it's the sum to k terms that I've assumed. So all of those terms, I can substitute in k on 2k plus 1. Now I've got some algebra to play with. Nicely, the denominator in the second one is already factorised for me. So we can get a common denominator, 2k plus 1, 2k plus 3. So the numerator becomes k outside of 2k plus 3 plus 1. All right. I'm just having a look at what we're trying to prove. Okay, we're close. Top of the fraction, 2k squared plus 3k plus 1. Yes, indeed, that top does factorise to be 2k plus 1, k plus 1. 2k plus 1's cancel. That's what I was trying to prove. K plus 1 and 2k plus 3. So yes, the result is true for k plus 1 if my assumption was correct. So if it is true for n equals k plus 1, we now tie that together with our first step and we induce the solution So yeah, since it's true for 1, it's going to be true for all of the integers by induction. All right, 6n, we'll have a go at some induction questions there.